let's go for the lecture today. So as I mentioned that last time we was looking at the language from the point of view of structure, of syntax. Today we will be touching the idea how the semantics can be encoded, and we will speak about one of the major and general approaches for today's machine learning using vector representation. Before this, I think that as you had the course on information retrieval, the first task will be easy for you, but it's the step towards understanding of the other steps. We will speak about the simplest search engine and how it works. Then I will speak about distributional semantics and how it then implements in the vector space models, and then just maybe if you didn't cover this in information retrieval course, you will know new facts about how latent semantic analysis is presented, is done using machine learning, and just a small lab on machine translation. So we have a long day today, so let's go. As we discussed, let's make breaks each hour, and so we have around 45 minutes to go. So first of all, let's speak about the problem statement. So why do we need these kind of semantic things and so on? If we have a single text, it's easy to hire a person to understand and explain the meaning of the text. When we have the bunch of million or maybe billions of texts, so it's the, for example, 10 to the power of 11 means 11 billion. So 100 billion. It's the approximate number of documents indexed by search engines like Yandex or Google. So text documents. I don't cover images or whatever. So there are 20 billions of images also and some bunch of videos. And we have these set of documents. And after you understand how big is this number, you understand that it's impossible to make humans to process this. What should you do? For any task related to these texts, you need to provide kind of a tool to do this. And no matter which task do we have, there should be an approach to this task. Usually, we have at least the task for searching kind of relevant documents. Relevant is very, from information retrieval course, you remember that this is a very badly defined concept. So usually we state some kind of a query, which is a text in natural language, or maybe some kind of other query. For example, for images, it can be text for images. For images, it can be image for images. Even for text, it can be like image, and you search for text documents. That can be the case. But usually, in this case, if we speak natural language processing, we have a natural language query to some documents, and we expect some kind of relevance. And here, relevance is very, as I mentioned, poorly defined term, because relevance itself, by the definition, is kind of a subjective measure of a human that the document solves the problem. So you take the problem which you need to solve. For example, I want to know how the Grover's algorithm work. And to do this, I will search for some query. So instead of setting a problem as a query, I set a text as a query. I say that Grover algorithm, just from my previous experience yesterday night. And whatever will appear is ranked by me, whether it answers my question or not. Even if I open like Wikipedia article and I don't understand this, it means that the document was not relevant for me. And if the document is more or less about what I wanted to know, then it's relevant. The same can be done with respect to freshness, for example. And for information retrieval, again, you remember maybe this concept of freshness. But if I ask just what can be American elections, so the fresh topic. If I want to know about the fact how the elections are run, so how they are executed, so what's the procedure, it will give me the Wikipedia article, but definitely what I wanted to know is who won at American elections. And the documents which are totally relevant in terms of like the maybe a year ago when I wanted to learn about American elections, today will be totally irrelevant just because they are not fresh. Okay, so the relevance concept is very tricky, and every time you build a system, you adjust your metrics, adjust your loss functions, you adjust your everything for this task. So if you want the search engine, it should do one. If you want the question answering system, it should do the second, and so on. So relevance here is very poor concept. There are two approaches how to obtain the relevance. The relevance in terms of binary function, so it's either relevant or not, or sometimes ranked relevance. So it can be from 0 to 1, somewhere in between. And then you can rank the documents. You can put the most interesting documents to the top and less to the bottom. And applications are enormous. So you can use this collection for mining of scientific texts, looking for dates of birth of some important persons, and so on. So multiple applications together with how this text can be generalized to solve the bigger problems. So for example, for topic modeling, it means that you can see what these texts are all about and what's the structure among the texts. You can understand who is the author of the text by style analysis of the text and so on. So, but here you need algorithms and maybe understanding of semantics of the text. Okay, so just to maybe to cover it again, let's remember what's inverted index. The implementation of this data structure is very simple. And actually, in terms of language modeling, it doesn't require even a language model. So it's implicit in this case, but we will see how it expands later to a language model. But when people were creating this kind of data structure, they were not thinking about language models. It was just a very simple task. Actually, this data structure was proposed in one of the this classical books on the art of computer programming. I think the first or the second book. So it was very ancient, like 1960s. So what's behind? You remember that our language is very interesting thing. So yesterday we spoke about the fact that language is a set of sentences in the language. And inside this description, so you remember there's 5 different blocks. There's a terminal symbols, non-terminal symbols, productions, all the stuff. There is the thing which is called terminal symbols. And what is interesting about the language, being infinite in terms of the language itself, it is finite in terms of the terminal symbols. The number of words we use in our language is limited. Of course, this is the fuzzy border, because words appear, words disappear. But if you take a snapshot of your language which you use, you know only a limited set of words of Russian or English language. So always the set of terminal symbols is limited. And if you speak about the big collection of text, just all the words used in this collection. And what appears that the number of such words is pretty small. There's like sometimes sayings that the Russian language has, for example, 1 million of words, or English language has 500,000 of words. Actually, what we use is around tens of thousands of words. And there, if you ever passed the tests in Facebook about what's the size of your vocabulary, maybe you remember that the numbers are usually around 100 of thousands of words. This number of words is still pretty big. And sometimes to build an inverted index. So by the way, do you need an explanation what's the inverted index? I think that I can swap the slides like this. Yeah, so I will start from this slide and then return back. So what's the idea of inverted index? Actually, in the Donald Knuth's book, it's not referred as inverted index. It's called the secondary key indexing. The idea is very simple. So imagine that every text is represented by the words which it has. So it's like an interesting feature about the text, which can appear in one text and can not appear in other texts. So, for example, word philosophy will never appear in like children's book, and that will distinguish children's book from the like adult books. And that's why considering such features can be important to like split the collections of texts. So it's secondary key, let's call it. So it's not unique, but it's important in terms of distinguishing. So you take these all words used in the text and use them as features, and then you cut the words. They create the pile of all possible words and put them in the table. This table is called a lexicon. So this picture, like without the cutted paper, is taken from the interesting book. You can Google for it. Actually, it is called the Algorithms in Computer Science in Real World. It's pretty old book, I think 30 years. But it's very handy in terms of when you had the course of algorithms, maybe you thought about what about using these algorithms for practice? And in this book, they're given the answers for this. So there are some pretty good algorithms applied to real world. So you'll know how the archivers work, you'll know how the compression works, and so interesting things. So the picture is from there. It's my reference. So you cut the words into the lexicon, and then for each word, you create what is called the posting list. So why it's called inverted index. So if you look at the like forward representation, the text is represented by words. So you have a text and you have a collection of words representing the text. So you, let's say, imagine that your text is a list in Python and you apply a set operation to this list. So you squeeze it to just a single representations of words. And this is vice versa. You take the word and you list all the texts where the word is present. Okay, so posting list is the list of texts where this word appears. Definitely the posting lists among themselves can be intersecting, but they are more or less unique. So for each word represents its own set of texts. Of course, posting lists don't usually store the text themselves. They store the indices of the text in the collection for compression. And then these indices refer to document files. Depending on the block size, just imagine there can be two options. You have, let's say, this is the SQL database, the DBMS. And you have the texts as the cells, the rows in the collection. So you want to build an index. This index will refer exactly to the column, to the row in the database. So posting list will consist of the numbers of rows in the database. The granularity can be smaller. You can attach also the offset, saying that there are sentences, and you refer not only to this particular cell, but also to some offset of some particular sentence in this document. So depending on the granularity, you can vary. So the information in posting list can vary, and the exactness of match can be increased. Among all these words, there is a law. Maybe you heard about this law. It's called the Zipf's law. Did you hear about it? Who can explain what's the law? Okay, you don't know. The Zipf's law is very, it's an like as everything which is not a law actually, which is a hypothesis, is very, not proven, and actually I don't know how to prove such kind of statements, and that's why it's law, not a theorem, not a hypothesis. Statement about the properties of natural language, and then it's reapplied to other areas in the world. So the idea is very simple. The person called Zipf, I don't know his name, he proposed the observation. He said that if you look at the natural language, and if you take all the words, and you take the big collection of texts, you compute how many times each word appear in this collection. That's a simple task. And then you sort by the number of appearance. And you will observe that the frequency of appearance of the word is 1 divided by the rank. So the first word will appear in some number of texts, let's say in every text. Then the second word, second most frequent word in the language, will appear in half of the texts. The third most frequent word in the language will appear in 1/3 of the text, and so on. And this here you see this kind of a curve falling down. So you see the words ranked by order. Yes, so it's the ranks. So they are ordered by the number of appearance in the texts. And here you see that here's the frequency. And frequency drops down as 1 divided by n. 1 divided by n, where n is a rank. Okay, what can we say in this case about the words? In this case, we can say that the words which are very frequent, this area, so let me maybe use other color to be more. So let's look at this part. So the words situated here, they are appearing in every text. What does it mean? They're in the posting list of this word in inverted index. There will be every text in your collection. Okay, and whatever query you will make to your data structure, there will be no difference. This word will never distinguish your texts. They are all including this word. Like for example, in English it will be the word the. In Russian it will be the word, I don't know, na. So some prepositions, whatever is used in every sentence. And that's why these words have very low resolution power. Okay, so for majority of queries, they will not help you to find the text. Okay. On the other hand, there are words which are very infrequent. Okay, and that means that their rank is pretty big. The frequency is low, and whenever you ask anything to a database, there is a high chance that there will be no such word in the query because they are very infrequent. So like names of chemicals, surnames of not well-known people, and so on. So why on earth this should be a good resolution power? And everything which is in the middle having the better resolution power. And whenever you have this square root of n, it has the best resolution power here. Okay, so why I showed this slide? Because of the next idea. So remember, we're speaking about the representing texts in terms of their meanings with the word. So we search for queries to be relevant in terms of something. Let's state on the fact that they are similar in terms of meaning or in terms of some kind of semantics, not well defined here. And we use words to capture this meaning. Okay, previously we used parts of speech to capture the meaning. Now we use the words themselves. And what is important here is we want to reduce the tails. Okay, how can we influence the tails in our language? There are a few approaches. First of all, we can glue the words. So why would we like to glue the words? For example, we have the capital letters in the beginning of sentences, and the word lion will be from the big letter and the word lion from the small letter. They will be different just because they have the different character set. But of course, this is the same line. So we can case fold it to the lowercase or to the uppercase, up to you. Second, we can do bringing the word to the initial form. It can be either a stem or a lemma. From the previous lesson, you remember that stem is unchanging, not changing part of the word, like here, and lemma is the initial form of the word. There are multiple algorithms to do this. So the Porter and Snowball stemmers developed by Porter, they both are, I think, the most widely known, Porter stemmer and Snowball stemmer, for Russian, for English, for other languages. And also you can find the other implementations in Natasha and Spacey for your languages. And also there is the PyMyStem, which is the wrapper of Yandex implementation of lemmatization. which is pretty good. So it shows very good numbers even now. Even it was developed by first developed by Ilya Segalovich. So you remember that Ilya Segalovich died long ago, and still this library is used in Yandex for monetization. Next, cutting the tail with high rank. So usually there are words which are very highly ranked in the language, and you see them. There is the to, the, be, or, and so on. So all these things. Uh, each time you apply any technique, you should understand that this is always the kind of a contradiction. So you want to make your life better, so you want to do the resolution power of your system better, but you always, doing any kind of such a technique, you throw away some kind of important information. I think we lost Danila. He's sleeping. No? Я не сплю. Хорошо. Okay. Then still, applying stop words is very important because, as I mentioned, the posting lists for big collections of texts will be of the length of all the documents. And imagine that you need to store 1 billion or 100 billions of numbers just to represent something with no resolution power. That's why stop word lists are a very important tool for pre-processing of the text for any NLP task. So here you can find the pretty good starting point, because you will expand your own stop word list for your particular tasks by this link. For example, here I didn't find the words like который, которая, которую, and so on, because they are very frequent in the spoken speech, and for some tasks it's good to remove these words. Here in this list there are no such words, so I extended it for my tasks. And here we'll find the link shared by Darina Dementieva, our former student, who is now the NLP student in Skoltech, PhD student, and she prepared the combined stop word list for English. Very good. I can just only recommend you not only the list itself, but her channel, which is referenced here. And also there are some kind of different other gluing techniques. For example, working with thesaurus, so gluing the words by their meanings, so finding synonyms and other hand-built clustering of words. So if you think that they are the same, you can cluster them during the processing phase. And of course, what is also done frequently, that the words with high rank, meaning that with very low frequency, are just not considered in the model. This can also be the case. So if the word is met once, it can be removed. For search engines, it's a bad thing, but for training the models, it can be the case. Okay. So I showed you these slides in the reversed order, and what is important. So for now, just to sum up, maybe you lost in my explanation. I was moving in the reverse direction in the slides. What's the idea? First, we have the problem. We have multiple texts. Okay, we need to somehow process these texts. What has been processed to do something? So the obvious task is to find the texts which are somehow relevant to our intention. So we have some kind of intention. We want something, and we want the texts, like the group of texts, which we can then work with, like as humans, as engineers, as researchers, and so on. So there should be a first step, relevant text. We apply the hypothesis that the text is represented by the words. This is very, very frequent hypothesis in different applications that is used. We then use this idea to build words as the secondary key for texts. And we build a data structure called inverted index or inverted file to store this idea. So the keys becoming the keys in some dictionary, the text becoming the values. And when you want to search for something, you grab the words from your query, find the posting lists, and then you do what? Remember, if you have multiple words in the search query. Guys, information retrieval, third year. So when we have a query of 2 words, and each word has its own posting list, what will be the result having both of these words?
Intersection.
Wow, great. Thank you very much. So you do the same. You take the query as a text, you process it, you stem it, you lematize in the same way as you did with the texts. You then grab the posting list from the data structure and intersect them. Perfect. And as obtaining the posting list is the constant time operation, because you can use a hash map, for example. Then intersection is the linear operation with respect to the longer posting list. That's why it opens the big question for a larger collection. So the longer is the collection, the longer is the posting list, obviously. And that's why inverted indices disappear now. They can be used only for medium sized data sets. For large scale data sets, inverted files, they are not very efficient. And then it's just to show you the idea that to store this kind of data structure, you usually don't fit into the RAM. So you store it on the hard drive, and here you need some kind of idea about storing. And this is again the picture from somewhere. But the idea is actually the storing the sparse matrices. Whenever you heard about sparse matrices, it's a number of matrices with a low number of non-zero elements. So a lot of zeros everywhere and some elements here. The same here. So if you imagine each word as a column, for every text, there will be only a small subset of words used to represent. So that's why you can use linked lists and different continuous structures on the hard drive to represent posting list. Okay, so let's move forward. And I would like you to solve the very, first to study the code and then solve the simple task. Let's say, here is the code. I hope you can see it. It's the code which shows how to use stemming and all the stuff and tokenization with the NLTK library. So NLTK library is the one which is, let's say, the classical. And there are some few texts which are already in the repository, so you can use for your experiments. So like the Old Man and the Sea, which is a pretty short book, the Man of Goodwill, which is a pretty long book, one of the longest in the world. It's like in the rank of the longest books. And here are some techniques to show. So for example, there are 2 ways to do tokenization. So one is here showing that exactly we are applying the English punctuation. So this is the explicit way to do the tokenization. Or you can do it in an implicit way by the default some tokenization in LTK, which is actually the same. So you will see that observation is exactly the same. So with both methods, the number of tokens is exactly the same. Here is some code to remove punctuation, because usually punctuation, it's not for all the models, but usually punctuation is not encountered in the what is called full text indexes. And here is how to apply the stemming. So just there's a stemmer dot stem and word. Okay. So these are the examples, and here's just an example which shows that how the stemming procedure aggregates the word, so how it glues different forms of the word into a single one. So for example, here it glues not only the same part of speech, but also different parts of speech. So the verbs together with the adjectives. And so on. Sometimes it can make mistakes. That's what you should always understand. Anytime you rely on algorithms for natural languages, they sometimes make mistakes, and these mistakes can be like 10%, 5%, 1%. Just be ready for this. For example, I don't know whether it can be somehow processed, but the word pound, you understand that in English it can be either whatever. So there are different meanings of the word pound. Okay, so please study this example and solve the following task. The task is, can I present it from here? Yeah. Please build an inverted index for this data set. So it's the set of facts. And your task is to do the following. So you take the texts, you split it into tokens, and get the stems of these elements. Then you prepare some kind of an index. You don't have to prepare it efficient. So there is a small text. So just think about it as a collection of texts and so on, a collection of tokens. Hold it in some data structure, just which allows you to restore texts by the words. And then write the code which allows you to process the complex queries. So you consider query again as the posting list. So as a list of tokens, and then you just will consider intersections of these tokens with other collections of tokens representing the text. And then just check your search engine given these test queries. So I can give you, I think, 15 minutes. If you have any questions about implementation, how can we do this, please ask. I will pause the recording for now and take your time. Please share your outcomes, whatever you want. So let's speed up. Oi. Can you still hear me?
Yes.
Yes.
I pressed airplane mode on my laptop, and I was thinking that the connection will fail. Okay, great. So let's continue. As we just spoke about, that somehow the relevance of documents can be expressed through the words. So can we propose some kind of a formal explanation for this? Let's speak about semantics and the way of representing semantics. Let's then think about the inverted or the forward index, depending on whatever you build. So documents to words and words to documents, as about the metrics. I already mentioned that the storage procedure of inverted index, which is usually discussed in information retrieval course, is very similar to sparse metric storage. So you can refer to how they are stored. You see that this is actually the same. And here comes the idea that let's think about this as about the metrics. And these metrics even have a name. The name of this metrics is called the term document metrics. Again, maybe from the course of information retrieval, you remember this. This metrics is usually sparse for short text. So the shorter is the text, the less elements are marked for each of the words. In this metrics, like again, usually about the convention. So you see that from these screenshots, you can see that there are multiple different ways of doing this, but usually documents are considered as columns, words are considered as rows. And if you remember the linear algebra course, or maybe you have some intuition about this, the matrices can be thought like in two ways, maybe more, but let's think about matrices in two ways. First, usually it's thought as a collection of vectors. So you can either see the collection of rows or the collection of columns. And now, if you look at the columns, and where you remember that the columns are documents, you will see that each column is now the vector representing a document. So in the intersection, there will be some number. In our case, from the inverted index, they will be zeros and ones, representing either presence of the element or not presence. There can be some other numbers, we will see which numbers, but these are the initial things, so the vector of zeros and ones, representing the text. From the other side, if you look at the term, at the word, you will see what? You will see again the vector of the length of the number of documents representing the text. And what is the interesting property of this vector? If the words are met in the same set of texts, they will have the same vector. That's an interesting observation. So the texts are, the set of text is the same, and the words distinguish them in the same way. So they are connected with the text in the same way. Maybe it can be somehow connected with the semantics of the word. And the second thing is, this is an operator. Any matrix is an operator. Operator means what? If you put the matrix to the left and the vector to the right, then and you multiply them, you will obtain the vector. So in our case, if you imagine the vector of documents, vector of the length of the number of documents, and put 1 in the position of the particular document, this is what is called one-hot encoding. So you put the 1 in the position of some of the documents, and you multiply this term document matrix by the document, you will obtain what? Obtain the set of words representing this. So it's like kind of an operator, which brings the document into the space of words. Okay, you just imagine this. There is a space of representation of words, and there is a document. And when you multiply one by the other, you get the vector of representation. Okay, just maybe a coverage here. To improve the idea of relevance, not just by representing text by the words, there is also a fix which considers the fact of the Zipf's law, which says that the frequency diminishes with the rank, and the resolution power is different for words with different ranks. And term frequency is showing that the more, like this is the obvious observation, the more times the word is met in the text, the more influence on the, let's say, the content of the text. So if the word, again, philosophy is met in the text for 20 times, definitely this is a philosophical text. And the bigger is this number, the more influence this word should give to the word. So in the term document matrix, you can put the number which is equal to the count. Unfortunately, there is the thing that the number itself will scale with the length of the text. So then we should normalize it by the length of the text. So the better to scale it from 0 to 1, the frequency. Yeah. So instead of just the count of words divided by the length of the text. Now it's normalized, so all the vectors have the same amplitudes for the words. Then sometimes this scale is not also the only, because having this proportional scale will distinguish between the word, I don't know, philosophy met 100 times and 200 times. The size will be twice different. Okay, this is not always the case. So if you want to distinguish between rare words and frequent words, you should pay more attention to small numbers and less attention to big numbers. To build a function which pays attention to small values and less attention to big values, you can apply a logarithm function. Okay, so it grows fastly in the beginning and then stops to grow in the large numbers. Then applying the logarithm, you slightly equalize the influence of 1,000 and 2,000 words. And also the second thing is that the resolutional power, the power of how good the word in distinguishing the text. And this is called the document frequencies. How many times this word is met in all the collection. So I mean, in how many documents this word appears. If the word appears in all the documents, then it's a stop word. It's a they, is, nu, and so on. And we try to, first of all, not to include such words into the indices, or otherwise we fight with them with this logarithm. If the n is the number of texts and the denominator is the number of documents where the document is met, then it will be 1 by 1. it will be logarithmical 0. So inverted document frequency will be 0. The influence of such text is nothing. Okay, it's 0. And the metric which can be put into the number into the cell of the matrix is multiplication of the importance of the term inside the text by the importance of the term inside all the texts. Okay, term frequency by inverted document frequency. Great. I hope you remember this. So let's move to the first glance on the semantics. We just represented both documents and text as vectors, okay? And they are called the concept vectors. So we will further consider this. And there's an assumption that concepts are orthogonal. We will speak about this later. And what we know, each concept, meaning the word for the text, expresses the single dimension in the vector. The element of the matrix corresponds to the weight of the concept, so how big this word or concept influences the semantics of the text. And how do we measure the similarity now? So previously we were doing intersection of two bags of words. How can we measure now the relevance for such vectors? Who can propose? There should be a distance metric, some distance metric. Who remember?
Cosine.
Cosine. Any other observations? Any other ideas? So yeah, let's go through this fastly. So this is the multidimensional space in terms of three concepts. So three concepts: education, finance, sports. There are some texts represented in the space of these concept vectors. And you see that there's a query, which is like very collinear to the sports education vector. What the model of vector space model doesn't say, it doesn't say how to define the concepts. So we said that the words can be the concepts, but there is an orthogonal assumption. And we know that some words are met together. For example, there are phrases like New York. You meet these two words in a sequence frequently, meaning they are not orthogonal. What does mean orthogonal? If you take the vector of one concept and the vector of other concept, in our matrix is what? So that's a row. Yeah. So the concepts are rows. We take two vectors and you multiply them with the dot product, you will get 0. Yeah, that's orthogonal. And if you meet the words together, then the dot product will be non-zero, because at least if in one text you meet two words together, then the multiplication will be more than, or like in our case, more than 0. So they are not orthogonal, just most obviously. Hussein, you have a question?
Yeah, so I'm a bit confused. Like, what's like? So we started with the term document metrics, right? And then we started with the term document matrix. This is the first thing we started with, right?
Yes.
And then we calculated TF-IDF scores.
Mm-hmm. And put them into the metrics.
So what's, I mean,
yeah.
I don't understand what's concept. I mean, what's the vector of concept?
Yeah. Okay. Let's get back. So as I mentioned, there are a few things which we will discuss later. Maybe my way of delivering is not the best here, but let's say that we're trying to define some kind of vector representation for words and documents. And if you have the metrics like this, like on the slide, you will see that you can consider metrics as a collection of vectors. Okay. And the document is defined through the words, and the words are defined through the document. So there are two ways of looking at the vectors, like this or like this. Next thing is that
I totally understand. Like, I mean, I'm pretty good in linear algebra, but I mean, what I don't understand is what's the, I mean, when you say concept vector and you want them to be orthogonal.
Yeah, let me this continue. So here is the model. So if you look for Wikipedia for vector space model, it says that let's represent the texts in some vector space. Okay, so it's the idea of vector space model. And in the definition, there will be the word concept. And this concept is something which is not defined. And that's 2 slides later shown on the slide. So what we see that here, for now, internal document metrics, we observe that the documents are defined through words. So for now, we can consider words as concepts. Okay, so concept is a non-defined thing, but if we try to map term document metrics to the vector space model, we observe that concepts now are words. Okay, this is the mapping for now. We will get we will remove this mapping further, but for now, concepts are words. And if we follow this procedure, so if we look at the model and say what we have here, representation as vectors with concepts, something. Okay. Second, there are some weights in the concept. Yes, we did it with TF-IDF. We put some weights, not just zeros and ones, but some weights. And also some similarity metrics. And just you proposed to apply cosine similarity, okay? Cosine distance, because we need a metric. Similarity goes from 1 to the close and distance from 0 to the close. But unfortunately, in the model, in the vector space model, there are some assumptions which doesn't match with our implementation. And the first assumption is that the concept should be orthogonal. And I'm trying to explain that if you take 2 lines in this matrix and multiply them with high probability, the dot product will be more than 0. Okay?
Yeah, I was just confused because so you're saying that we're assuming that concepts are orthogonal, so now it makes sense. But I thought that we already defined concepts, so that's why I was confused.
No, there is no definition.
Yeah, it makes sense.
That's the problem. So the model itself have empty spaces in terms of definition. So the model says that there should be some concepts and they should be orthogonal. So the weights, again, so no definition for how to define the importance in the model. And so the model doesn't define the metric. So we need to somehow introduce it by ourselves. And I think that you remember the slides from information drill course. I hope they were shown to you. And here it shows that depending on which way of normalizing the TF-IDF you took, it can be the problem, for example, to work with the Euclidean distance as a metric. Because for longer texts, it can generate the vectors of the longer vectors with the longer norm. And then Euclidean distance for short text will be smaller than actual semantics influence. So if you have 2 short texts, they will be close in latent space just because they have short vectors. Like here, imagine that I draw this vector and this vector. They look in the opposite directions, like in very different directions, but they're close in this distance, even if these 2 vectors are actually the collinear vectors. So some metrics should be wisely chosen with respect to the way how you define the importance, the weights in the metrics. So that's why cosine similarity looks an interesting choice, because it encounts the fact that the vectors can be of different length. So here is definition, and let's stop here. So at least maybe not exactly following the vector space model, we found the way how to represent the text with a vector. Okay, so now we represent text as a vector. We introduce the relevance metric, which is the cosine distance, 1 minus cosine similarity. And these 2 things together say what? We can do relevance search. So whatever we did in your lab. So when you do the intersection of posting lists. So you can look for relevant texts with the mathematical procedures. You have dot products, you have cosine similarity measurement to obtain similar texts. You see that the mathematics solve the problem for content retrieval. Yeah, so the some kind of semantics appear here. So you mean English language and you obtain the sentences about English language. What is bad about this, that for this kind of representation, which we got here for now, we need to do, like, you have the dictionary of, like, lexicon of hundreds of thousands of words or tens of thousands of words. And to do the dot product, to compute the cosine similarity, you need to run lots and lots of computations just for a single distance computation. Pretty, let's say, computationally expensive. So let's do something with this. And we go to these two approaches, which tries to solve multiple problems with vector space modeling. So remember, we are trying to define semantics of the text through numbers. Distributional hypothesis. Let's look at these at any term document metrics. And as I mentioned, there can be some concepts, some words which appear together. And that means that they are somehow speak about the same. So if we meet in the same text, I don't know, cats and dogs, and they are in all the texts are meeting together, that means the cats and dogs are about something similar. So they're about animals, pets, or whatever. If we meet the word integral and derivative in a set of text, and they meet are in this, the set of posting lists are highly intersected. That means that derivatives and integrals are semantically about similar things. Even if they mean different things, they are, in terms of described domain, are in the same area. And if you take the cat and integral, the intersection of posting lists will be most probably empty set, because it's very hard to imagine the text where cat and integral are met together, maybe except the texts about quantum mechanics, where the Schrödinger cat will appear together with some integral equations. And the hypothesis, the distributional hypothesis, is the idea which appeared long ago, around half a century ago, or maybe even a century ago. And it says that the words which are distributed in the text similarly have similar meanings. The words which occur in the same context, they have similar meaning. And the short form is the last one provided by Jonathan Firth, which is said that you should know the word by its friends. Okay, so let's define again some important thoughts about distributional hypothesis. Again, similar context and same distribution are not well-defined terms. The context, for example, can be defined through the bag of words, like just you take the text and say that the whole text is a context for the word. Or you can define it as a near context, saying that like in word2vec, it will be just a couple of words to the left, a couple of words to the right. Again, the context is not very well defined. And also, but still, this idea that similar distribution and similar contexts influence the meaning similarity is still the most powerful idea for natural language processing. So it's the thing which is inside any model, including BERT, including transformers or whatever. Transformers are trained on the sentences. Sentence is a context for the word. Just similar words are appearing in the similar context will get the similar embeddings in the transformer mechanism. The consequence is that two words which are similar in meaning definitely fail the vector space model. So they are collinear, not orthogonal. And what is the consequence? So can we try to define the orthogonal basis for our vector space somehow? If we have multiple, so let's say we have multiple synonyms in the language, what if we try to get rid of these synonyms? What if we glue them somehow automatically? Maybe by dimensionality reduction. So the idea here is that there should be a latent space. Okay, so we have the vector space model saying that there is an orthogonal space. And this orthogonal space previously, like what we thought is the space of all the words, but this is multidimensional, 100,000 dimensions. Let's try to make the number of dimensions smaller. Let's build a hypothesis which will reduce dimensionality, speed up the cosine similarity computation, and together solve for us the problem of orthogonality. This is done in latent space, latent semantic analysis by searching for lower rank approximation of the matrix. What does it mean, lower rank? Lower rank, that means that there are only few linearly independent words. So the rank is the number of linearly independent rows in the matrix. And for now, if you have the query vector, like some words defined by one-hot encoding, there is a term document matrix. If you multiply them, so if you previously normalized it, so this multiplication hides what? Cosine similarity. So multiplication is what? Is A, B. So two vectors are multiplied. So for each row, so for each column, sorry, for each row in the matrix, we multiply our vector by this row. And if we norm it by A and B before, so in advance, then we have cosine similarity as a result. So yeah, so this division can be done in advance. So our term document matrix is normed row by row. If you want to bring all the vectors, which are here, so A is here, B is here. So A divided by norm of A will be stored in the term document matrix instead of just A. So we do pre-processing in the beginning to put all the vectors onto the sphere. Okay, so they're all with the norm of 1 now. And we want to do the low rank approximation. What does it mean? We want to split our term document matrix into 2, which will be of the lower rank. Okay, and it will give us what? So if term document matrix is just, imagine, let me draw. For now, the procedure looks like this. Imagine we have the vector of query, which is, let's say we have 10,000 words. Okay, 10,000 words in our lexicon. So 10K. Okay, so there is 10K here. And that means that this matrix is 10K here. So the words are here. And here are the documents in this dimension. So the documents will be, let's say, 1 billion of documents. Okay, the overall size of the term document matrix is 10K by 1 billion is 10 in power of how many? 9, 12, 13. Okay, pretty big matrix to store. Okay, that's why we do low rank approximation. So we first try to find the smaller dimensions, we try to reduce the size, and we try to find the orthogonality together somewhere. And that's why we'll build it into the form of multiplication. Now we have the vector of Q of the same size. So it's 10K here. As multiplication should be preserved, so there will be 1 billion here. 10K here first, but these numbers are not yet defined. Okay, and this is our rank. So this is the rank, the number of independent rows. So this number is the same for matrix multiplication. So it will be 1 billion by n by 10K, 10K by 10K. And this number can be chosen somehow. Maybe you can run some kind of search or whatever. But let's say this number is now 1,000 or 100. So the dimension of dimensionality of our latent space is 100. So now to store this matrix, we need 1 billion by 100. So it's 10 in power of 11 and 100 by 10K, some epsilon. So 1 billion, 1 million actually. And this is much smaller than 10 in the power of 13, okay? So 2 orders smaller. So doing low rank approximation, we save the space. We try to find the approximation of latent space, having this latent space, latent semantic analysis hypothesis that there is such a space which is orthogonal somewhere. And if we find such an approximation, we can prepare the vector of query in a lower dimensional space. So if we multiply this vector, which is 10,000 elements, by the projection matrix, which is 100 by 10,000, it will be 100 elements. So our word will be mapped into this small space. Then this will be used to search for text in the same space. Okay, so we do what with these matrices? Let's again, so we have two matrices, and here comes the queries, here comes the texts. Okay, this matrix projects the queries into the like words, right? The words of queries into the low dimensional space, and this matrix projects the texts into low dimensional space. They do a projection matrix into the same latent space. That's why it's latent. We don't know this space. It's hidden somewhere. And there are two matrices which will help us to find these the representations previously unknown. So the last thing is to find what? This. So no one said how we split the matrix into two parts. And I hope that I heard from the students that one of the most widely discussed topics in Innopolis universities, more frequently in discussion, are conditional probability and SVD. So actually, principal component analysis is actually the tool which solves exactly the problem. It looks for major directions in the multidimensional space, which represent the space better. And if you keep only the best distinguishing directions, and they will be orthogonal by the definition of the method, then you will have this latent space approximation. PCA is done using singular value decomposition. I will not stop here. I hope you remember what is this. If no, just read about it. SVD is the way of decomposing the matrix into three. It's the two unitary matrix and one diagonal matrix. And as this decomposition is exact decomposition, there is the low rank approximation hidden here. So you can cut the parts of this diagonal matrix with singular values and make the rank of the matrix small. So this is the SVD. So just try to convince yourself that this is what actually solves the problem. This is how you can do it. There is the code example for like I wrote the explanation for how SVD works and in terms of reducing the dimensionality. And let's sum up. So we are almost in the end of the second hour. First, we define the vector space model. So what it says, there is a tool which represents the documents in a numerical form as vectors. That's always cool because like if you can take the object, the entity of the real world, and map it into the vector representation or any mathematical representation, and you assume that this representation preserves the property of this mathematical thing. So for example, it can be multiplied by the number, it can be multiplied by other vector, it can be transposed and so on. Then all the power of mathematics of the previous centuries starts working for you. So we obtain the vector for the document, and wow, cool, we can do linear algebra things with these vectors. Second is that, so we said that there is a vector space model. Second, we use distributional hypothesis to find the insight. So vector space model, unfortunately, didn't give us the answer for the question, the words are orthogonal or not. Distributional hypothesis says definitely words are not orthogonal. If there are synonyms, if there are words with similar ideas encoded inside, that means that they will be represented as the similar vectors in the space. And that means that if the vectors are collinear or near collinear, they are definitely not orthogonal. Then comes the procedure called latent space analysis. What does it say? We will try to observe the latent space which satisfies the vector space model. Okay, distributional hypothesis give us an insight about the collinearity of the vectors. Latent space analysis says that we will apply low rank approximation with orthogonal vectors for our initial representation to solve the problem of orthogonality, and also together solve the problems with storage, with the computational speed, and so on. So multiple positive effects here. And principal component analysis and the SVD, singular value decomposition, as the engine for this method, they give us the answer how to introduce the latent space analysis. So is this like set of ideas clear now? Maybe not with details, but yeah. The question? No, you're wonderful. I hope that I just explain the things which you already know, but still I want you to be clear in the future that how these things work. So about orthogonality and other things. What can I say else is that latent space analysis deserves some critics. So first of all, even optimized version of principal component analysis are very slow, especially in CPU. There are ways to speed up this, and you can go by the links to see how it's approached. So actually, matrix decomposition, the intermultiplication, is a very, very important task in machine learning now, and how it is done, it's very important. And maybe you know that even on the next level of mathematics, when we speak about convolutional networks and tensor operations, again, tensor decomposition. So tensor train is kind of analog to SVD for tensors. And these decompositions and low rank approximations are extremely important to bring down the size of the models to like at least imaginable things. So for now, deep networks are very deep. And if you want to take the trained model and save it into a smaller amount of memory, tensor low rank approximations are doing the same stuff as low rank approximation is doing here. That's why there are algorithms which try to speed up the procedure of decomposition. Second, like obviously it requires all the data to be used. Okay, so you cannot do SVD without all the examples of the data. Second, that PCA has the assumption about the distribution, saying that the distribution of the initial vectors in the space is normal by some x. So you can always find the direction, which is called the principal component. So the vector along which the elements are distributed normally. So there's the head. But unfortunately, this is not true. It means that actually it cannot always be correct thing. Obviously, if you think about how the words are distributed by the Zipf's law. That's why there are some other alternating ideas which tries to fix the problem. So first it's PLSA, which encounters the fact that distribution along the axis can be different. So we can apply any distribution instead of normal. And second is LDA, proposed, I think, a little bit later and popularized by Andrew Ng. Maybe you know this person for the machine learning course in Coursera, about the other way of thinking of representing the metrics of concepts. And also, there's a big problem with adding new words and new text, because if you want to just grow the metrics to the left or to the right or to the down, you need to recompute all the stuff. So there is a big problem with fine-tuning of such models. So what's the approach? So how can we influence all these critics in some way? to do latent space analysis with machine learning. It means that we will try to close our eyes on the mathematics and say we don't want to think about orthogonality, let some machine learning technique do it for us. And also, we will try to deal with the fact that we need all the data to train the SVD, for example. And here comes the set of models which you should be familiar with. The first one, which came 7 years ago, in terms of my life, it's nothing. In terms of machine learning, it's actually the first days of the era. So because like you know that the reborn of machine learning occurred in 2012. So the people started thinking about machine learning as a useful handy tool only 8 years ago. So it was the first year after when people started paying attention to machine learning again. So word2vec is not actually the single model, it's the collection of two models, which consider the distributional hypothesis, you remember, about the context. The words in the similar contexts have similar meanings. And there are two ways of representing the context. So it's always the context around the word, but the models are trained in two different ways. In the skip-gram model, we try to predict the context by the word. So given a word, what will be the near neighbors of our word in the text. And the continuous bag of words model is doing the opposite task. By the context, you try to predict the word. Actually, this is what, for example, the statement of this problem is very similar to the statement of BERT. BERT, again, it, given a masked sentence, we try to predict the words in this sentence. So the statement is very similar. Here are some insights. So it's the slides from Information Theory course, some insights about how it works. I just want you to stop here. We have a very simple neural network, actually with one hidden layer. That's very cool because like you can obtain the good result only with a single layer network. And what is single layer network actually? Input layer is what? It's a dictionary size vector. Okay, so it means that 10K here. Okay, output layer. What does it mean? Output layer is again the dict size vector because we train prediction of the word by the context, and that means that it's again one hot encoding of the text. So this is the text, the original word represented by the one hot encoding. This is the predicted context represented by the one hot encoding. So this is 10 by 10K. And here's what's the neural network layer? So how can you represent the neural network layer? What's the layer of the network? In terms of mathematics?
What, one? Two.
What is two?
Input and hidden.
No. The layer, the single layer of the artificial neural network is the matrix multiplication plus sigmoid function. Okay, so you multiply this vector, so A by B plus sigmoid function. Okay, that what's the layer? You multiply weights by the vector plus apply sigmoid. So and here appears another vector. So your vector is now multiplied by the weights, and hidden layer is actually the place which learns latent space. On the hidden layer, if you set the number of neurons on the hidden layer small enough, again, 100, 1000, you will learn the internal representations by training this network. Okay, so here is the what is called the embedding. What you remember that? So there is we use the term vector, and in machine learning you heard about embedding. So embedding is the vector. What's embedding? In Russian, it's like putting into, to embed something. So embedding means we embed the concept into the latent space. So we find the place there. We try to find the position. And this procedure is embedding, and the result is also called the embedding. So the vector of the concept in the latent space. So we obtain the same, you remember previously, there was a matrix and the vector, and we obtained representation here. Here we do the same. We obtain representation here, but the only thing added is sigmoid here. So it's a non-linear thing. So we again obtain the vectors, which are representing the text in some latent space. I hope at least the idea is somewhere here. Continuous skipgrams another way. Again, there is a place to find the embeddings here. Very similar. The bonus for word2vec was a hype about latent space arithmetics, because they observed that similar relations preserve similar relations in this vector space. So the vectors with, like, say the royal woman and royal man will, like, the royal relation will be encoded with a similar vector difference. It worked, first of all, only for the limited set of examples, but it was enough to present. And second, you don't have to forget that actually the dataset was trained. Sorry, the model was trained on the dataset, which tried to optimize exactly this metric. So what they did in their training phase, they were trying to predict this kind of relation. That means that it's not like a big deal if you train the model to do the task. If the model works, it solves the task. So here it's the embeddings themselves are just the, how to say it, the additional bonus for the results of the paper. So they were trying to solve the problem of predicting the relations, and embeddings in the hidden layer were just some side effect of the training. There are some problems of this kind of model, which you should remember about when you address these kind of things, when semantics through the vector representation. First of all, the general problem which is still addressed in the models is out of vocabulary problem. So in training phase, the words which are not in the vocabulary or not frequent words are usually encoded with a similar vector, with the same vector, like some predefined fixed vector. And it means that whenever you will search for a rare concept, you will most probably find something irrelevant. So only frequent words are used for embedding. And today it is approached with a subword tokenization. You can read about this technique. So actually in transformers they are used. So when you take the unknown word and try to represent it in subword parts, which are like limited in numbers. So you take the vocabulary of words and vocabulary of subwords for those words which are not present in the dictionary. Also, this model didn't address grammar, abbreviations, forms, and all the stuff. And it only worked for words. So actually the embedding was for a single word, not for text. So yeah, there were first approaches to do this with averaging the vector. So you can use word2vec to embed the text, the whole text. But unfortunately, it was just averaging. And with averaging, it's always the pain when you have the long enough text. The average is also the average vector. So it means that whenever the text is long, you will significantly lose in relevance because it just tries to converge to the average vector of all the vectors. Later, this problem of the fact that word2vec didn't address text embedding, so vector representation was done only for words, not for texts, was addressed with doc2vec. It has the simple but a powerful thing. So in training phase, together with the words, it was also the marker for a paragraph. So each sentence was marked with some separate number, and it helped to build the embeddings of the whole paragraph, so the sentences. This technique was the first technique, doc2vec. I think it was 2013, 14, so it's very, very soon after word2vec, which addressed the problem of embedding of the text into the vector space model with neural networks. details, training phase. Okay, here the task was slightly different. So they considered the problem of the previous task. So they trained for different other problems. You can search for other models. This is all history. And here I want you to do a simple lab. Oh, so it's not even the lab. I think that this is the other lab. Let me see what's here. No. So NLP semantics. Just a second. Oh yeah, here is just the example of how to use Word2Vec and Doc2Vec for training and for embed. So let's look at the code just fast. So here for Doc2Vec, the most widely used implementation, the GenSim library. Here is how to initialize the Word2Vec network and train it on some data set with some epochs. And here is the same for Doc2Vec. You can import the model, train it with some parameters. You see that here is the collection of documents, vector size. You remember this is the internal layer, the hidden layer size. Window size, it's the distance between target word and the, so it means that there's a 5 words context taken. So 1 plus 2 plus 2. Min count is the address for the problem of out of vocabulary. So you to bring down the size of the dictionary, you just remove the less frequent words, and the words which here it means that we consider all the words, but usually this number is around 10 or 5, meaning that the words which are met less than 5 times in all the collection of the text will be omitted. And workers is the parameter which says how many threads will you use to train the model. So that's ways of initializing the network, and you can train it by for your task. So you should imagine, consider here the very important fact that there is no English language. Whatever you train, whatever you use, is the representation of the language used in the collection of text you use. So you remember that the language itself is the infinite set of sentences. Yes? And here we train the model on a limited set of sentences. That makes the contradiction. Yeah. I have something here. So someone wrote in the chat. So let me see what's in the chat.
It's me. I'm sorry. I need to leave. I need to take the test.
We will have the break soon.
Okay.
So I just make the comment and we will go to the break.
No, the doctors came for the test.
No, I mean
I cannot. I have to leave.
Not because of you, but because of the break. So just the thing to consider that whatever model you train is a representation of the language you train on. If you train on tweets, it will be the Twitter language. If you train on the fiction books, it will be a fiction book language. If you train on newspapers, it will be newspaper language. And you remember that even then, when we spoke about the parts of speech, and we see that as for the brown corpus is the corpus of the magazines and newspapers. There are corpora of other texts, and they behave slightly different for solving the task with natural language, just because the language itself was different in the input. So here, whatever you use for training is your language, and don't expect that the model trained on Yandex search queries will work good on the fiction books and vice versa. Okay, so this is a very important comment about whatever problem you consider, you should be using the data for training of this language. So this is how to train the model, and there is also the, I think somehow it was the inference phase. Yeah. There was a task to complete to do the embeddings, but we will skip this problem to move further with some lab. So let's make 5 minutes break after my comment, and so in 11:17 we will meet and continue with the last part of the lecture. Okay.
Sorry, I just have a question.
Yeah, sure. You can ask questions.
So like, is there any instance where SVD is really successful with text? Because, for example, if we just go and grab something like the last chat of like 100 people and do SVD on it, probably like all eigenvalues will be very small. So, I mean, you won't have you won't have good concepts with high singular values to be able to shrink your space. I mean, like, is there some instance where SVD was successful?
Like, for example, which you provided, the answer is obvious. So like there is the big problem of SVD, which is the pain. So like let's state the fact that singular value decomposition has a very good power for big matrices which are dense. Okay, so if there is a dense matrix with big number of elements or any number of elements by each dimension, SVD can do the job. The problem with the real life is that the matrix is usually sparse. Your example is that you grab the 100 of tweets, means that there is the 100 of texts, and the number of words used in this text is pretty big. So it's usually 100 by something, by times 2, times 3, or whatever. And the matrix will be sparse. SVD is very bad with sparse matrices. Any decomposition is very bad with sparse matrices by the only reason they are very sensitive to small changes. Okay, when the matrix is sparse, any slight change in the matrix, one value which appears, completely ruins the embedding. So that's why these usually, if you build kind of recommendation system or search engine or embedding, there should be another approach to do this for dense for sparse matrices. So if someone says that, like I had this discussion in Yandex, I think a couple of years ago, about my problem. So we had the data, and it was always the question that how many items do you have, how many features do you have, how many elements are marked in the matrix. So if the matrix is big and it is pretty dense, then ALS, for example, for decomposition, or SVD for decomposition can do the job. If the matrix is sparse, no one will help you. Only other methods of recommendation. Did I answer?
Yeah, I think it's more about like, I mean, you can have sparse matrices and still like decomposable into very small ranks, but I think like in real life, it's very hard to.
Well, they're definitely
craft it.
composable, but they are useless.
Yeah,
No,
probably. I mean,
the composition give you the good orthogonal representation. It gives you some orthogonal representation, but this is representation of whatever sample you have. It's not the representation of semantics.
now that I'm thinking, for example, if we for example get like bills, let's say bills from supermarkets, and build some matrix about like what items are being bought and stuff like that. I mean, even if the matrix would look sparse, but I think it should work properly. But I mean, with normal language, I think it won't work. It mostly depends on like.
Maybe because the bills of the supermarket have the different properties. They're more stable, and they have, for example, less like language. Like if you take the language, what is usually done is 100 to 1,000 dimensional representations. Yeah. So like, for example, in BERT, you have 768 dimensions for the vector. So meaning that still the semantics of the language is hidden in pretty pretty big dimensions. So no one argues that you cannot represent the semantics of the language with 10-dimensional vector. You will lose a lot of information then. If you think about the, let's say, humans shopping somewhere, it can be that there is a very small number of behavior patterns. So people buy, for example, eggs and milk together all the time. And with a high chance, even a small sample of examples can give you the pretty good observation of how humans behave in the supermarket. That's my idea. So it may be wrong, but that's how I think about the problem, that even the sparse matrix here can be pretty stable, because it's actually, even the sparse matrix represents human behavior.
Yeah, that's what I wanted to say. Like, I mean, if there's some stability, as you described, even sparse matrices could be decomposed in a sort of useful way.
Yeah. Oh, we're, I think, done with the break. I didn't have a break, so let's go further. The last part. Let's go fastly, because we have only, I think, 40-50 minutes left, and a couple of slides also. Like the question, like the democracy. Do you want to try to do the embedding with Dr. Vec as a lab right now, or you will keep it as a home experience?
For me, it works as a home task, not as a part.
Okay, so if there are no volunteers to do the job, so anyway, we can finish earlier, because like this is only the idea. So we have this kind of model which I asked you to download. So why did I choose the Dr. X? Let me explain. Actually, the ideologically, using neural networks to embedding texts into latent space is like, the idea is similar for both Dr. Vec and for BERT, for example. So whatever you apply is apply neural network to feed forward the text and get the embeddings. So that's why we don't bring here the enormously big models for BERT for good embeddings. And also this kind of, let's say, example is enough to show the idea. So it will still capture the patterns in the word. And please study the example, and please try to run this code. You will see that there's nothing special. You put the preprocessed text, and you get the vector as a result. So actually, what I wanted you to do here is to like, again, to summarize. So previously I said that there was the vector, so there was the inverted index. Inverted index is what? Is actually the squeezed representation of text through the words. And intersection, if you think about intersection, is what? If you have the text represented through the words, yeah, so there will be zeros where the words are not present, and the one where the words are present, okay? And if you have two texts represented by the words, if you have some positions intersecting, the intersection, the size of the intersection is equivalent to what? To the dot product. So you multiply this vector by this vector. Whenever the position matches, you will get 1 here, okay? So the more the number of intersections, the bigger is the dot product for two vectors. So actually the algorithm of inverted index is the simplest form of dot product of the vector with zeros and ones. Okay, so mathematically it's equivalent thing. Then we developed the idea that there can be not only ones, but there can be 0.1, so 7.4, for example, and so on. And we preserved the procedure. We still have dot product here. So we still multiply the vectors. And next, we squeeze the vector to the significantly smaller size with LSA. So there's a latent space. So this was the explicit space of words. Now we have the latent space of smaller dimension, and we still do the dot product on this vector. So the procedure is exactly the same. Nothing changed in the idea here. So that's why this example was only to show that if you take the, let's say, the Lexems vector and embed it with Dr. Vec, you will, instead of these words, obtain the vectors, and then instead of doing intersections, you will do dot product. Procedure is exactly the same. Okay, you understand? So let's go forward. Sometimes it is good to think about the efficiency of your systems. If you remember, even word to vec is what? Is a neural network. Neural network means matrix multiplication. Sorry, vector to matrix multiplication. If your dimensionality of the matrix is some hundreds by some thousands, it still means that there is a time to compute is proportional to the size of the matrix if you want to run a dot product. So n by m. And these kind of activities steal your CPU time. Yes, today neural networks are very efficient. And today the forward pass of the deep network still fit into some milliseconds. So for example, the FPS of some network can be 20 sentences per second, whatever. But this is still a fully loaded CPU. And if you do it as a part of your big infrastructure, for example, of search, yeah, when you have 30 millions of requests per day, so you just can compute 30 millions of requests by 10 milliseconds, you will get 300,000 seconds of fully loaded CPUs to process just embeddings for texts. It's a pretty big deal. So you need a lot of computers to do this. Of course, for a small desktop application, this is not the big problem. But when you scale, you understand the difference. And that's why sometimes the idea lays on the top. Instead of, like, as we discussed it in the very previous, like the second, I think, lecture, what is a possible way to represent the artificial intelligence is to memorize the function. Instead of trying to somehow find the computational procedure, you can memorize the results together with the inputs. And if you want to embed the words, you know that there is a limited set of words, let's say 100,000 words. And you know that the embeddings for these words can be of the 500 values dimension. So meaning that, let's say 500 values, 4 bytes per value, 2 kilobytes for the row. 2 kilobytes for 100,000 words is what? 2 megabytes and 200 megabytes of data. So you need only 200 megabytes of your hard drive, not even a gigabyte, megabytes. You can load this as the part of your program in the RAM with the constant time embedder. So the program will put the key, the word, into the hash map and obtain the vector of the embedding as the result. So the model itself is small, yeah. So the size of the RAM you use is very small, 200 megabytes. The embedding speed is enormous. It's constant time. It's like go to the dictionary and retrieve the value by the key. Yes, it limits slightly the application because it only embeds the words, and you will still need to do a couple of steps back to the past when the Dr. Vec wasn't implemented. You need to average. But if you work with the short queries, with the short requests, this is enormously useful technique to use pre-trained vectors, and you can obtain them here from fast text You can obtain them from Natasha, from Rose Victorious. You just take the model, and you have the dictionary which works fastly and returns embeddings for your words in a constant time. Just know about this opportunity. This is the slide, I think the deviation. I use these slides in the information retrieval course. But what I wanted to say here that the models of embedding, they evolve. So here, for example, DSSM, the model from Microsoft, adopted then by Yandex and improved significantly, addresses different problems of the past. So it, instead of just words, also adds trigrams to fight with out of vocabulary problem. The application was done to solve the particular task. So the network was designed to solve the task of search. So previously, we were trying to build the language model, so some latent space representation of the texts, and then solve the problem of retrieving documents, which is similar. But we were assuming that the relevance is just the cosine similarity, the similarity in terms of words. Yeah. And Yandex said that firstly Microsoft, when they were designing Bing, and then Yandex, then when they improved the model, said that actually, if we want to do search, let's train on the search task, not try to just build some embeddings and then try to benefit from them. But let's try to solve the problem. Let's try to solve the problem of search. And what they used, they, instead of, if you remember, what was the architecture of word2vec? There was a vector and the vector of these dimensions. And actually, you can consider that it's a matter of discussion, but there is no supervision. The context itself, the texts themselves, are used both as the training examples and the target values. So you take the sentence and you decompose it into the training part, like the x and the y, f of x. And this is kind of an unsupervised learning because no one gives any markup saying that this is correct or not. Just the application practice. So people use sentences. This sentence, if it's grabbed from somewhere, it's correct sentence. No markup. In DSSM, both companies approach the problem. They said that we do search. We want search relevance. We want answer the questions with texts. And instead of targeting the prediction of the context, they targeted the kind of first approximation of relevance. They said that let's consider the document relevant if the person who did the search clicked on the link. If the person, by the action, approved the fact that the document is relevant. We now, like 5 years later, or even a couple of years later, know that this is a bad approximation. So click-through is not the only metric, and it correlates, definitely correlates with relevance, but it is very leaky in terms of different attacks. So for example, did you hear about clickbait? So what's clickbait? So bait is like what you use to catch the fish. You throw it into the water, fish finds this food and grabs it. It's called the bait, наживка. Yeah. So a clickbait, it's something which tries to catch your click with some bait. And this usually the form of the texts which are very intriguing, which finishes with nothing. For example, do you know what Donald Trump does last year? Or shocking news about Elon Musk at the masquerade. So some kind of thing which can, what? Seriously? And even if it's not relevant to the original query, it can be the catch for you. You can click. Other type of context is just clickbait by its nature, because the pornography is usually clicked without any relevance to the original query. So if you show porn or cats to some any query, there will be people who will click just because they, oh, porn plus. And that works. And that's why the clicks themselves is not actually the only. Can you hear me, Hussein? Guys, can you hear me?
Yes, we can.
Yes, yes.
It's like Hussein wrote that the sound is dead. I think he reconnects. Sound check. I think that it was some kind of problem with connection here in university. Because it kicked me also. So to sum up, if you want to train the model for search, try to use the data for search. That's pretty, I think, a good idea. Okay. I cannot remove all the drawings. That's strange. So we will proceed with these drawings on the on the slide. And later, I think Yandex did some work to improve the model. They extended the library. They changed the target slightly. They use some techniques as hard negative mining to improve this, but still the idea is the same. The embedding is done for the task. So yes, you can use it for other problems, but embedding the texts with these models doesn't necessarily work for other tasks. Cool. I cannot even use the eraser to erase the contours. Okay, so we'll proceed like this. So you can also see other models which were following the similar approaches. Then this is what I will not again stop on for a long time. I think we're moving close to the end slightly. Is that the transformers, they got back to the original approach. So instead of using recurrent networks, the attention mechanism, which is slightly different, is used to catch the near context. And the models like DSSM, the previous model, was unidirectional model. And for now, there was like the word track was the bidirectional context. Then there were multiple LSTM like recurrent models which were unidirectional, and then now we go back to the bidirectional context. What is important? I want to find like the match between the previous lecture and today. So again, to emphasize, last time when you tried to answer the questions with the syntactic approach, you were playing Chinese room. You had some set of rules. You don't understand what's going on. You just follow the parts of speech and you substitute the words into the positions of some, like in some places. You know that if you ask about persons living in Innopolis, you should search for sentences which actually met in such kind of sentences. So no semantics, just syntactic similarity. This approach, the syntactic comparison, was widely used and I think is still used in some applications for machine translation. So actually there were multiple ideas of what is machine translation, like what should it look like. There were ideas about interlingua, so intermediate language. There were ideas about the structural semantics. And when I was a student, I was also the student of a translation department. I was a student who studied translation. There was even the class on comparative syntax of Russian and English languages. So what we studied, that how one construction in Russian language morphs, like how it evolves into the English language and vice versa. So why people do this? Because this formal way of thinking about the texts is actually the key to translation. If you can take the sentence in Russian, build the syntactic structure, you know how the syntactic structure changes into English syntactic structure, then you just translate the words, the parts of this sentence, and you got the translation. And you remember all, I hope you met this in your childhood, translators like Prompt, which were doing the task in this way. So they were morphing the syntax, they were doing translation of single words. There were some other improvements with statistics, so which statistically, like, not single words, but maybe phrases are met together, so they are translated together as a phrase. But the idea of translation was structural. It was exactly the way how you did it in your homework. So it was looking at the structure of the sentence, translating words by the dictionary, and reproducing the sentence in the other language. Since 2017, I think that the idea appeared that semantics is somehow represented in the latent space. And also the second idea that there is a shared semantics. So if you can say the word in English, you can find the place in the Russian latent space for this word. So there maybe there is a common latent space for the words. And this is what actually Google started with. And I think Yandex is catching up. So they, in 2017, they also introduced the hybrid mode of machine translation. That let's try to work with sentences as with the semantic instances instead of syntactic instances. So previously we used syntax to translate and the dictionary to just map the translations. Now let's look at the semantics of the sentence and try to reproduce it into other language. So the models look like you have the embedding space and you have multiple inputs for multiple languages, and you train this space onto different pairs. Let's say that English to Russian, French to German, English to French, Chinese to Russian. And by training multiple pairs of languages, you estimate the common latent space, common for all the languages, and you can use it for multiple pair translation. So, and this is very helpful when you translate from the pairs, like in the pairs of languages, when there is not a big amount of parallel text. So when you cannot train the separate model. And this is what, for example, in the lab of Adelhan, Albina Safeeva is doing. So she's building a translation mechanisms for the languages which are rare, which have very small number of parallel texts. So you understand that, for example, for a Tatar language, the majority of parallel texts are like Russian Tatar. So there are texts which are in Tatar and in Russian, maybe Arabic and Tatar because of the religion. But English Tatar, I think not a big portion of text. Ukrainian Tatar, not a big portion of text. But if you want to translate in these pairs, you can use the idea of shared semantic space to do a translation. So that's what came to the translators, like the translating companies as an idea, and is developed for the last, I think, 3 years in production. Okay, so I want you, for now we have like half an hour left, so let's spend some time. I think that this is like the very last slides in this lecture. I want you to do a very simple task, to obtain the developer key for Yandex Translate and to use it for translation between different pairs of languages. Okay, so there's nothing to add. You just only need to proceed with the key, obtaining the key, and try to play with this sample. So this is the small portion of code. It worked for me. Sometimes what I mentioned that what I noticed last years, that the syntax of this library, the Yandex Translator API in Python, changes. So sometimes it cannot work if you have the previous version. So please update it to the last, and this code will work for you. Please try it in your pairs of language, Russian English, Spanish English, if you speak Urdu, Arabic, or whatever. Try this. And I will give you, let's say, 10 minutes for this task. So try to play with different pairs of languages. Okay, and I'll put the recording on the pause.